Hello, this is my video lab report for Lab 1 Constant Velocity. So the purpose of this lab was to take a video of an object moving at constant velocity, meaning it's moving at the same speed and the same direction, and then to use the tracker software to analyze the video and track the position along a time interval, and finally use Newton's second law to model the position versus time. And the main result of the lab was that the model was a good predictor of the observed position versus time. So this is a video in tracker. It's just a soccer ball being rolled across the ground at constant velocity. And this is the position versus time graph that it created. So these are the formulas that I used for the models from Newton's second law. So there's the net force formula, which can be written as mass times the change in velocity over the change in time, which will be 0 because the change in velocity is 0 for the ball. And then this is a position update formula and the velocity update formula, which I will use in GlowScript model. These are some of the data points that I had. So there's mass, which equals 0.45 grams, but it's not needed in this lab because the net force is 0, so this whole part of the velocity update equation will cancel out, and so the mass is not needed. And then there's the final position and initial position at time 0.617 seconds and 0 seconds, which can be seen in this table. And then I use that for the average velocity, which I will be using as my initial velocity since it's all the same. And then so that's displacement, which is final position minus initial position over the change in time. So that turns out to be negative 0.88 meters per second in the x. And then delta t, I use 0.016 seconds. So in GlowScript, this is where the initial position is. This is where the average velocity and also initial velocity is. And then I have the velocity update formula, and because the net force is 0, this is just saying that the final velocity equals the initial velocity. And then here is the position update formula, which will be used to graph position versus time. And here's what it looks like when it runs. So there's the position versus time, which is a negative slope line. And then here is the velocity, which is constant. And when I graphed the model data and experiment data, you can see that the model is a pretty good fit for the experiment data. They're similar, they're pretty close, except for here at the beginning there's some differences and along in some other parts, but most of the time they're pretty similar. And then some of the reasons for it not being perfectly aligned is human error. So when I plotted the points on tracker, I may have not perfectly plotted the middle of the ball, and then also when I cut down the video, I may have not removed the part that was accelerating or slowing down, so it may have not been constant velocity the whole time. And then when the person pushed the ball, they may have pushed it a little bit outside of a straight line, so that could have changed the velocity. But generally, it was a good fit. And for the what if question, so if I were to flip the x-axis from, so I use positive, if I were to flip it to negative, that would change the slope of the graph, so it would just be positive sloping instead of negative sloping, so the position would have increased as time increased instead of decreasing. And then for whether it is possible to say how many forces are added together to give a net force of 0, it's difficult to say exactly how many forces are coming into play to make the net force 0, but we do know that some of the forces, such as gravitational force and normal force, those will balance out, and then applied force and friction force will balance out. Although it's not clear exactly how many there are, we can see generally these are going to be the forces acting on the ball. That is the end of my video. Thank you.